Yeah, thank you for the invitation to speak here. I cannot see Ellen, is she here? Oh, there. Is the sound a little high? Maybe. So it's a great pleasure and a privilege to speak at this conference in honor of Ellen's 70th birthday, and to do so here in the house that Grothendieck built. Yesterday, Marco was saying that the speakers was chosen to represent various parts of Ellen's vast work. And so apparently it falls on me to explain her work in K-theory. And I will talk about this fiber square that came out of work by Bloch-Esnault-Kerz. So let me see, maybe can it fit here? So Bloch-Esnault-Kerz, there's some restrictions on what they prove, and then the full statement was proved by Ben Antieau, Antieau-Mathew-Morrow, and Thomas Nikolaus. And Beilinson also made some improvement along the way. So let K be a complete discrete valuation field of characteristic 0 with perfect residue field. K of characteristic P so if this is a smooth and proper map, of formal schemes. Oops. Then the following square of a billion groups is Cartesian. So let's see if it can fit here. So we take K naught of X and P complete and invert P, and then now we map this to the same thing for the spatial fiber. Then here there's a crystalline Chern character, and we can identify its image with, or its target with the Rham-crystalline homology of the generic rigid analytic fiber. And inside here, there's this piece, part of the Hodge filtration. Here, and the statement is that this is Cartesian. I'm just going to write that here. So this means that an element here lifts to the to this formal guy if its Chern character lands in this part. Okay. Yeah. You can also ask the question if instead you have a smooth and proper scheme over spec OK, and this is the formal completion along the special fiber, then how are their K-theories related? And that's difficult. So, yeah. Okay, so so Antieau-Mathew-Morrow and Nikolaus promote this to a Cartesian square of spectra. Whoops. So here we have the K-theory, and here we have the Rham homology. And here we have the this piece of the Hodge filtration of the Rham homology. Okay. Well, other shifts, yeah, like this. Okay. Okay, so yeah, so we would like to know that if we take pi naught, we get the thing upstairs, and
not only it's not obvious that it's Cartesian.
Can I finish? So so we take pi naught, and the difficult thing is to know that this becomes injective, and it does because the Hodge to the Rham spectral sequence collapses. Which is a theorem of Peters-Scholze. So, yeah. Okay, so how can we produce this? To do this, we replace it by something else. Namely, instead of K-theory, we take TC. And here, instead of this the Rham homology, we take negative TC. And here we take periodic topological cyclic homology. And now here we have to Nygaard complete these. Okay, so so this is what I'm going to explain, what these things means and how you get this square. And yeah, and then it's a calculation that it gives you that, and maybe I will not say so much about that. Yeah, should I also write here where this indicates Nygaard completion. Okay, so so let me first explain what algebraic topology is. So this is the six-functor formalism on anima.
So could you please repeat what this, I mean, this k, because you have small k, big k, I mean.
It's written on the board.
Yeah, but the square, I mean, it's all, the bottom line, they are all big K.
Yeah, they are all big K, yeah. So anima is also what is called homotopy types, or Lyric calls it spaces, but this is not a good word. And the word anima, I think, is due to Dustin. And so Clausen and Scholze have introduced condensed sets, and sets sit inside condensed sets. As the discrete condensed sets, and the inclusion has a right adjoint. So this preserves co-limits, but it does not preserve limits. Anima, by contrast, sets sit inside anima as via a left adjoint. Via a right adjoint. So this functor here preserves limits, but it does not preserve co-limits. So sets instead, so anima are not like spaces. It's like sets with some internal structure, internal symmetries. And so sets are the anima that do not have this internal life, and so Clausen and Scholze call them static because they don't move. Yeah. So, but anima are discrete, and that means that if we have an anima, then sheaves on this anima is just presheaves. So this is just all functors from T or T up. It's the same, say, to spectra. So because T is discrete, a sheaf is determined by what it does on stalks. It's just a collection of its stalks. And also since anima are discrete, every map is étale, because being étale is a local property, and if you're discrete, yeah. So that means that if upper streak is always if upper star. And this common functor is just restriction along F. Well, that tells us that if lower star must be right conextension along F, and if lower streak must be left conextension along F. So this is a very simple six-functor formalism, and yeah, it's because of this simplicity, for example, that the Serre spectral sequence is much easier than the Leray spectral sequence is in general. Now, in any six-functor formalism, there are two kinds of duality. There's smooth duality and there's proper duality. So smooth duality is if this happens, and but in anima this happens always because every map is étale. So in fact we have this. So smooth duality is not interesting in anima. Proper duality concerns the norm map. So in any six-functor formalism, there's a norm map from F lower streak tensor some dualizing guy, which is called the Klein-Spivak dualizing object, to F lower star. So this map exists for every streakable map in any six-functor formalism, and it's completely canonical. And the thing that we call Poincare duality in algebraic topology is the statement that this map is an equivalence and this dualizing object is invertible. So this is not the same as Poincare duality in the six-functor formalism on topological spaces, where which is an instance of smooth duality. So yeah, let me also say what this is. So if we base change f along itself, here then this dualizing object is P2 lower star delta lower streak of 1. So you can see why you don't often see this in algebraic geometry, because in algebraic geometry the diagonal is very often proper. So then delta lower streak is the same as delta lower star, and this just goes away. And you get a map from f lower streak to f lower star if you're separated. So yeah. So, but now if this map is not an equivalence, or in general we then define Tate cohomology to be the mapping cone. Like this. So this is Tate cohomology. And yeah, so now the case that I will consider is that we take the circle group, which I will call U1, and then we consider its underlying group in anima and its classifying space, which is also an anima. And now the unique map from that to a point. In this case, this dualizing object becomes just a shift. So this square or this sequence here becomes f lower streak 1 to f lower star to this. So this functor here is what we call negative topological cyclic homology. This functor here is what we call periodic cyclic homology. This map here we call the canonical map. And in Kahn's theory of cyclic homology would be the fiber here up to a shift. But that's not the case here. So we will define a TC, and it will map here, but it will not be this.
So when you write these isomorphisms, are those definitions, or
these are definitions, yeah. I just don't allow myself to use equal. So this is this is not what that is. So we will define this, but we need something else first. Namely, we need the definition of a cyclotomic spectrum. So this definition in some form goes back to Bjerkstedt, Chern, and Madsen, but it was formulated in a much better way by Nikolaus and Scholze. So yeah, maybe I can do that here. So a p cyclotomic spectrum is a pair v comma phi. So now I should have prepared something, namely, so so U1 is an abelian group, so the pth power map is a group homomorphism. So therefore it induces a map here. And this diagram here commutes because it's the only thing it can. And so a p cyclotomic spectrum is such a pair here with V a spectrum with circle action, so such a functor from BU1 to spectra, and V, and phi is a map from V to the Tate along this map here from, yeah. Okay, so now I should try this. No. Here. Yeah. Yeah, let me give two examples.
And Lars, is it clear that this Tate construction you've made, it doesn't always commute with base change. So is it clear that this actually agrees with the Nikolaus-Scholze?
It is the Nikolaus-Scholze.
No, but I mean, you're doing a relative Tate for B1 going to B1. The factors there are B of CP and...
No, it does always, because we are in anima. So upper star is upper street.
Good, yeah.
But let me just say what Dustin was saying. So he's saying that there's a square like this. This is the cyclic group of order P, which is the kernel of that guy. So this has a unique base point, so we can consider this guy here. So if I take this and then pull it back here, then that's the same as pulling back and pushing forward here, because upper streak is upper star. So upper star and lower star satisfy base chains always in anima. And yeah, so the underlying guy is the Tate for the group CP of the underlying CP spectrum. Yeah. Okay.
So yeah. Let me also like this the norm is also compatible with this. When you talk about.
Let's not worry about that now. But yeah, so in this world, the integers has a Frobenius, and what is that? So we have the unit here to P lower star, P upper star, C. And this is just P lower star C, because P upper star C is C. And then we have the canonical map here to P lower star T, P upper star C, which is P lower star T, C. Yeah, so this map here is this is the Frobenius.
Does he mean the constant sheaf Z here?
It cannot mean anything else. Right?
Oh, yeah.
Yeah. So, yeah. Here's another example which is that if C is a stable dualizable presentable infinity category.
So is there anything special about Z? I mean, you can replace it by any spec.
Yeah, but I chose C for a particular reason, which will become clear soon. Yeah, okay. So if we have this, so this means that we have a co-evaluation here in PR stable. And we have an evaluation, and they satisfy, they exhibit this as the dual of the other. But I can consider this composite here, which is the dimension of C. And the unit in stable, so this is in stable dualizable infinity categories and co-limit preserving functors. There the tensor unit is spectra. So this map here is a functor from spectra to spectra that preserves co-limits, and that is determined by what it does to the tensor unit here, which is the sphere spectrum. And so that goes to something which we call Tate. And then this promotes to a p-cyclotomic spectrum. So now I have only defined it as a spectrum, but then what I'm saying is that in fact it has a canonical circle action, and it also has a canonical Frobenius, which is what was defined by Bøksted, Chern, and Madsen, or discovered by Bøksted, Chern, and Madsen, I should say. Okay.
Here is P a prime? Or is it
Yeah, P is a prime. P is a.
So what, is that just important in the definition? Or
Let's say yes. You can also, yeah. So there's also a definition of a cyclotomic spectrum, and then you have such a map for every P, for every prime P, but there's no, they don't interact with each other.
the definition is Frobenius. Does P need to be a prime?
Let's say yes, and we only, so there is a P in this talk, and this will stay fixed the whole time.
Ah, okay, so this phi is assigned to P.
Phi is assigned to P. And if we can do something more general, let's do it in the coffee break.
But so far you haven't
One last
used.
question.
So far,
You get this phi by this method of example one?
No,
No.
no,
Just you didn't tell us how you get it.
I don't tell you how to.
Oh,
Yeah, yeah.
but so far it's just totally abstract. You don't use anything of X.
Yeah.
Right. Starting from that board.
I've not used anything there yet. However, now what I'm going to do up there is I'm going to take C to be nuclear quasi-coherent sheaves on X.
And you tell at some point vaguely the relation with the TC minus and
The Rham.
with in the Hodge filtration.
Well, let's see. Maybe not.
So what's the question? Sorry.
No. So now there's an interaction between these two here. So see, this guy is connected, and is connective, and it's also co-connective. So therefore, this map here will land in the connective cover of this. Like this. And this I'm going to write like this, and think of it as a relative. So the Frobenius factors as a relative Frobenius and some other guy. here, and this greater than or equal to 0 here feels like it's relative to some Archimedean point, but I don't know. In any case, there's that thing. And now there's a real theorem, and that is Bjerkstedt's periodicity theorem, which says that this as a cyclotomic spectrum is Th8 of Fp. Okay. Yeah.
Z or -1 thing, just notation.
That's just notation, and I'm very confused if this should be a -1 or a +1.
Well, it depends how you look at it.
I don't know. Okay, so now we will begin to make the square. Or actually, yeah, actually I wanted to state 2 results of Nikolaus and Scholze, which are very general but very powerful. Namely the Tate-Orbit-Lemma and the Tate fixed point lemma. So the Tate-Orbit-Lemma so this is Nikolaus-Scholze. Says that if we have a spectrum with circle action, and if it's right bounded, then if we take the orbit, so push it forward with lower streak along the P, and then take the Tate along F, then this is 0 after P completion. And the Tate fixed point lemma says that if V is left bounded, no, then the analogous thing holds with P lower star. Like that. Yeah, so it's the orbit here is because that's this functor here is called homotopy orbits, and this is called homotopy fixed points in this situation. So now if V phi is a cyclotomic spectrum, which is bounded, which is right bounded, then we have this cyclotomic structure map. And so we can apply F lower star to that. And then it follows from the Tate-Orbit-Lemma that after we P complete, this is Tate along F. So we get a map here. which I'll also just call phi. So now you can see this goes in the same place as this canonical map we had upstairs. So now the definition of TC is that we take this, which is that, and now I'm going to P complete. Then here I have two maps. I have the canonical map, but now I also have this map phi. And so I can take the equalizer of these two maps. And that's the definition of TC. Yeah. So if we want to apply this in a geometric situation, then we should get some cyclotomic spectrum to apply it to. So, for example, if X is a QC-QS scheme, then its stable infinity category of quasi-coherent sheaves is dualizable, and so we can take THH of that and then take TC of that, and that's the definition of TC of X. So here in the theorem, if
maybe it's obvious, but you have to explain why this is bounded. Maybe it's QC-QS, but
yeah. If it's not, then we should assume.
No, it's bounded.
It's bounded. Okay, it's good. Okay, so. Here I'm not so sure what to say. I'm going to say QC-QS formal QC-QS map of formal schemes. So then TC of X is TC of nuclear. Yeah. But this is also understandable, at least if X is the formal completion along something. And so that this is actually the thing that shows up in the paper by Bloch-Esnault-Kerz, was proved by Adriano Cordova in his thesis, and the analogous statement for K-theory was proved by Greg Andreev. Yeah, thank you. Efimov, you're right, yeah. Yeah, it was proved by Efimov. Thank you. Yeah.
Could you please remind us how these are defined?
No, we can talk about it later. Yeah. Okay, so now we construct the square.
for the circle, the square.
So we begin with this relative Frobenius here. So this is a map in cyclotomic spectra, or p cyclotomic spectra, and the Tate fixed point lemma implies that for all V, for every spectrum with circle action, the induced map on Tp becomes an equivalence after P completion. Here I'm using that cyclotomic spectra promotes to a symmetric monoidal infinity category, and it's the tensor product there, which is the tensor product over the sphere. So, okay. No. Now, now if we look at the definition of TC, which is on the bottom of the top board, that's the fiber of a fiber sequence where the bottom term is TP. So now we have two TPs that are the same. So this will give us a square. Now we have to have a cyclotomic spectrum in order to be able to say TC. And it has to be bounded below in order, or it has to be right bounded in order for phi to make sense. Oops. So, but this is Cartesian for all cyclotomic spectra that are right bounded. Okay. So now we should work on this a little bit. Moreover, so let's work on this term here first. So TC minus C minus 1 tensor V. This I can map by the canonical map to TP. And the fiber of that is some homotopy orbit guy, and because V is bounded below.
Sorry.
Yeah.
Sorry, is it necessary? I mean, this bounded. Is it necessary?
Yeah.
And because it's a Z mod, it looks like a Z module, so somehow.
Well, there's no definition with if it's not.
No, but for Z modules, I mean, Tate-Orbit-Lemma is always true. I mean, because it's dimension monoidal.
I don't care if it's true more generally. So you can worry about that. So so if we invert P, then this map is an equivalence. Yeah. And now here, this is this map was already an equivalence before we inverted P. So it's also an equivalence after we invert P. So this corner here we can replace by Tp of C tensor V after we invert P. And now this, when we do that, then this composite map here is the canonical map. Okay. Yeah. Maybe to come back to Elaine's question, this is, so this canonical map here, this is what gives you this piece of the Hodge filtration. In that case, and because we have inverted P, well, actually we're not quite there yet. Let's see, so maybe I should get the top board. Yeah, also here, because C has the trivial cyclotomic structure, I can take the C outside. So this becomes like this. So here we tensor over the sphere with C, but we also invert. We complete a P and invert P, so then we can take it away. So this is just Tc of V. Like that. Yeah. Now we had written this horizontal thing here as this canonical map from Tc minus C tensor V here, and the fiber of that is some homotopy orbit term which has finite Nygaard filtration in each degree. So therefore we can, if we Nygaard complete both terms, then this square will be Cartesian.
So what do you mean by Nygaard completion?
the filtration induced by the spectral sequence. And now we can remove this because we are complete. Now we can analyze things on their graded pieces, and then we can get rid of the C. So this is also Cartesian. Okay. So now the only thing that we need to understand better is the upper right-hand term. And so
what happened to the completion on the bottom? I got completion on the bottom row there.
oh, thanks, yeah.
So in the square, you announced at the beginning you didn't invert P, which is very different from the originals. Maybe
Where did I not invert P?
in the horizontal bottom line of the square.
Yeah.
It's no longer on the board.
Right. But that's so I had to invert P to identify this term, and then also to identify this term. So it's only after I invert P that I have good descriptions of everything. There might be something better to say, and Jacob Lurie is working on that now, and maybe he will have some.
But then maybe I copied wrongly, because the square you had written the bottom line, you didn't invert P. I mean.
This one here, though?
No, it's no longer on the board, unfortunately.
Let's talk
about it later, of course.
I can look at your notes.
Yeah.
So let me just say here that if this is TH8 of some ring R, then TC of this is TC of, so by the Birklet periodicity theorem, this is TH8 of FP, and now we have TH8 of R. But TH8 is symmetric monoidal, so this is TH8 of FP tensor R. But this tensor is over the sphere. And now we would like to replace it by the tensor over R. And that's allowed. So let me just write it like this. One reason it's allowed is that there's a map from here to there, and that satisfies the hypothesis of the Dundas-Goodwilliam-McCarthy theorem. So we can translate this statement here into the corresponding statement in K-theory, and there it's true after you complete and invert P. So all in all, if we have a ring, we get a square like this. which is Cartesian, and now that will give you this square here. Okay, in the last 5 minutes, if we look at this square here, it looks like, is this a Bouville-Laszlo square? And yeah, so so let's see be an algebraically closed completely valued non-Archimedean field of characteristic 0.
Sorry.
Yeah.
There may be something which is not obvious. I mean,
Yeah.
you say that the second Cartesian square recovers the first, but how is it obvious at each map? Because now you have
No, it's true. So you also need to work to show that you actually get the crystalline Chern character.
Okay.
So yeah. Okay, so by Bhatt-Morrow-Scholze's second paper, if we begin with this square now for OC, here, and and we then take homotopy groups then we will have a diagram of graded rings. Now we can invert a Bhatt element then we have two periodic graded rings, and now we take the degree 0 part. Then we get here we just in the top left-hand corner we just get QP. Here we get the ring BE in p-adic Hodge theory. Here we get beta Rham plus, and here we get beta Rham. So so these are the global sections.
So maybe around these things are not completed, so it's like
It's completed. That's what the Nygaard completion does.
I mean, the definition of beta plus and beta.
Yeah, what about it?
If I remember correctly, they are not completed.
No, they are completed. You're thinking of B. Chris.
And they prove this. I mean, establish the square in a non-completed situation. I mean,
no, because then they are probably looking at cyclic homology and not topological cyclic homology. And then you get the completion for a different reason. Okay, so here, so this is the Fock-Fontaine curve. Associated with the tilt of C. So the curve only depends on this F, and then C defines a point on it. And so we have the curve, and then we have the open inclusion of this, of the complement of this point corresponding to C, and we have the formal completion there, and now we have this, and when we take global sections, we get that. Okay, sorry, I'm already over time. Let me just say finally that that now, if you have some yeah, I don't know how to distinguish between a German X and a curly X. So now it's a curly X. So this is some model over spec of OC, which is smooth and proper. Then we can do the same things, and then we will get a vector bundle here, a vector bundle here, and gluing data here. But we also have so we could also take this. So here we took homotopic groups, we inverted the Bhatt element, and we took the degree 0 part. We could also take homotopic groups and just take the degree 0 part, not invert the Bhatt element. Then this gives a different lattice, beta Rham lattice inside. And so in fact we get a modification of vector bundles, and from here we get a trivialization of one of them. So this is precisely the data you need to build the Hodge-Tate period map. And this is a suggestion or proposal of Dustin Clausen to build it in that way. Okay, so sorry I'm over time.
Are there questions? Or are there more questions?
Well, I mean, it's just a clarification. So maybe I wrote wrongly what you have written, but in the file, so you wrote the original fiber square and then the improvement here, and then you wrote your fiber square, and in the bottom line of your fiber square, the way I wrote it, you didn't invert P. It's true. I mean,
okay.
Immediately I remarked that, because here of course...
That sounds like a mistake.
Ah, okay.
Yeah.
Okay, because at the end you invert P. Yeah.
Yeah.
Okay,
yeah,
thank you.
Yeah.
I'm sorry.
Can you just elaborate a little bit about what you were saying about the Hodge-Tate period map?
Yeah, so the Hodge-Tate period, well, first of
Can I interject and say that I never made such a proposal?
what do you want to call it, suggestion?
I didn't. I don't know what you're talking about.
No, I mean, I even have an email where you write it down.
That's proof.
Well, Dustin, if you have forgotten already, it's life is longer. So okay.
So I have a question. So that big
Well, no. I'm answering his question. So put x instead of OC in the square. So then. Now, when we do the same things here, we will get vector bundles everywhere. So that will just give us a vector bundle on the Fontaine curve. But now there's another, so this is a beta Rham lattice sitting inside here, but there's another beta Rham lattice which comes from, it's actually the last proposition in Bhatt-Morrow-Scholze's second paper, which tells you that these two lattices are the same, but they don't sit inside this one in the same way. And so this exactly gives you a modification of vector bundles. Yeah. Centered at infinity, yeah.
Yeah, I mean, this z minus 1, this is like a Frobenius twist of z, is that the idea? Or let me ask you, saying what the idea is, do you know anything about its homotopy groups?
Oh yeah, because it's THH of FP.
Ah.
So it's a polynomial algebra on it over FP on a generator in degree 2. But let me just say something. So there's an analogous situation in the Bloch-Esnault-Kerz part of BMS2, and so let's see, so we can go here from dualizable, but now suppose that we have things defined over the p-adic integers instead here. So then we can make such a relative Frobenius. So we have the Frobenius here. But now it factors like this, and this. So cyclotomic spectra together with such a factorization of the Frobenius means that you take the circle action and you make this action of the subgroup of order P genuine. And Jeremy Hahn, Arpan Raksit, Alan Yuan, and Sanath. I cannot remember his last name. Sorry. So they show that now if you upgrade, so if you remember this whole thing here, and then do the even filtration here, then you will get prismatic cohomology as opposed to Nygaard completed prismatic cohomology. And so now with the C, we also have such a factorization here, and therefore it feels as if there's some base, but maybe some Archimedean base. I don't know how to think about this map.
Is the 5 prime some kind of divided Frobenius?
What?
Is 5 prime some kind of divided Frobenius?
No, it's like a relative. So you know, in your paper on the Durham-Witt complex, you have this thing and this.
Of course, of course.
Yeah.
But I was thinking of the Nygaard stuff.
Why does the Nygaard thing happen? I think it's this thing that
runs also don't take.
it's this thing that they discover in BMS2 that the Rham cohomology admits a Frobenius untwist, or yeah.
But for Z, there is a Frobenius from W2 of Z to Z, if you take bit vectors. This exists. Is there a link with what you're doing?
I don't think so.
No?
Yeah.
Okay.
Maybe he
but there's a question because when I raise it, I mean, because this is relevant to the question about Hodge-Tate. Because if I remember correctly, I mean, they say that this logic only, I mean, you have somehow to trace these maps. If I remember correctly, in AMMN, they say that somehow this logic only works for like this, not for general perfect field or something. I don't remember what.
Okay. Let's give people a chance to get some coffee.
Yeah, let's thank you.